Right now, at this very moment, you are falling through a hole in space 2 billion light years wide. This is not science fiction. This is scientific fact, confirmed in 2013, and most people still have no idea. We live inside the KBC void, a cosmic desert where matter is 20% thinner than it should be. This emptiness warps our measurements of reality itself. The universe appears to expand faster here than anywhere else, breaking our most fundamental equations about how the cosmos works. Today we'll journey through the discovery that shattered modern cosmology. We'll explore why 90% of space consists of hollow voids. We'll reveal what it means to exist in the cosmic outskirts, far from the dense concentrations of galaxies that populate most of the universe. By the end, you'll understand that everything you thought you knew about our place in the cosmos might be wrong, because we're not observing the universe from a typical location. We're observing it from inside one of the largest holes ever discovered. Let's begin. 3 astronomers were counting galaxies when they noticed something impossible. Ryan Keenan, Amy Barger, and Lennox Cowie examined data from 35,000 galaxies in 2013. They were mapping galaxy positions across billions of light years, creating a 3-dimensional picture of cosmic structure. The numbers didn't add up. Everywhere they looked near Earth, there were fewer galaxies than there should be. Not slightly fewer, 20% fewer. This wasn't a small measurement error or a localized anomaly. The pattern stretched outward in every direction for 1 billion light years, forming an enormous sphere of cosmic emptiness. And we sat near the center. This wasn't a small gap between galaxy clusters. This was a void on a scale that shouldn't exist according to standard cosmology. The team triple-checked their data, used multiple independent galaxy surveys, and examined the sky from different angles. The result remained consistent. Our galaxy and everything around it sits inside an underdense bubble of space so massive it dwarfs everything else we've ever observed. The void received a deceptively casual name, the KBC void, using the initials of its 3 discoverers. But there's nothing casual about what it represents. In the standard model of cosmology, the universe should be roughly uniform when you zoom out far enough. Sure, galaxies cluster together and leave empty spaces between them. That's expected. But a region this enormous, with such a significant deficit of matter, pushes the boundaries of what random chance can explain. Computer simulations of how the universe evolved from the Big Bang rarely produce voids this large and this empty. When they do, it requires exceptionally rare initial conditions. The statistical probability is less than 1 in 1,000. Some scientists calculated it would take a 10 sigma deviation from average density, meaning it's so unlikely you might not find one in the entire observable universe. Yet here we are, living inside one. The implications cascaded immediately. If we reside in such an unusual location, does that bias every measurement we make? When we point our telescopes at distant supernovae to measure how fast the universe expands, are we seeing the true cosmic expansion rate? Or are we seeing a distorted local version, skewed by the emptiness surrounding us? The void hypothesis offered an answer to one of the biggest mysteries in modern cosmology, the Hubble tension. For years, scientists have measured 2 different expansion rates, depending on whether they look at the ancient universe or the nearby universe. The numbers disagree by 9%. That sounds small, but it represents a genuine crisis. Both measurements are incredibly precise. Both should give the same answer. They don't. If Earth sits inside a massive underdense region, gravity from the denser matter surrounding the void would pull outward on galaxies within it. That would add extra velocity to their motion away from us, making the local expansion appear faster than average. Suddenly, the conflicting measurements made sense. We're not measuring the universe incorrectly. We're measuring it from inside a hole. This realization changed everything. But it also raised an uncomfortable question that cosmologists are still grappling with. If our location is this unusual, can we trust anything we think we know about the cosmos? Cosmic voids are not truly empty, which makes them even stranger than their name suggests. When astronomers call a region a void, they mean it contains far less matter than average. But matter still exists there. The void around us has roughly 15% of normal cosmic density. Picture it this way. If a typical region of space contains 10 galaxies in a given volume, the same volume in our void might contain only 1 or 2. The galaxies don't vanish completely. They become rare, scattered islands in an ocean of near-nothingness. Between these lonely galaxies stretches space that contains mainly dark matter, dark energy, and occasional wisps of hydrogen gas. The density is so low that gravity barely functions. Without enough mass to pull things together, structure formation essentially stops. No new galaxy clusters can form. No rich superclusters emerge. The void stays a void. This emptiness has consequences that ripple through physics itself. Gravity is already the weakest fundamental force in nature, requiring enormous masses like planets and stars to show noticeable effects. In a void where mass is scarce, gravity becomes even less relevant. The dominant force becomes dark energy, the mysterious pressure that accelerates cosmic expansion. In dense regions full of galaxies, gravity fights against dark energy, slowing down expansion in those areas. Inside voids, gravity loses that tug of war. Dark energy wins decisively. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward, while the filaments of galaxies around them act as walls. This creates a self-reinforcing cycle. The more a void expands, the emptier it becomes, which allows even faster expansion. Scientists confirmed this through careful observation. They measured how galaxies near void edges move compared to galaxies in denser regions. The void galaxies are rushing away from the center faster than cosmic expansion alone would explain. Something is pushing them outward. That something is the gravitational pull from all the matter outside the void. Think of a void as a valley surrounded by mountains. Gravity pulls downhill from the mountains toward the valley. But since we're talking about space rather than terrain, that pull makes galaxies fall outward, not inward. The effect is measurable and significant. Our own galaxy is moving away from the local void at 600,000 miles per hour, driven by this gravitational imbalance. The interior of a void becomes a strange place for physics. Light travels through it, experiencing less gravitational influence than light passing through normal space. This affects observations in subtle ways. When astronomers study the cosmic microwave background radiation, the faint afterglow of the Big Bang, they notice that light passing through voids appears slightly cooler. The reduced gravity in voids causes less gravitational redshift, showing up as cold spots in temperature maps of the early universe. These cold spots line up perfectly with where we observe large voids today. This alignment isn't coincidence, it's physics. Understanding what makes voids empty helps explain why they matter so much to cosmology. They're not just boring blank spaces between interesting galaxy clusters. They're laboratories where dark energy dominates and where gravity takes a back seat. By studying how matter behaves differently in voids versus dense regions, scientists can test fundamental theories about how the universe works. The KBC void around us might be unsettling because it makes us question our cosmic typicality, but it also offers a rare opportunity. We're positioned in exactly the right place to study the universe's most extreme low-density environments. The structure that contains these voids is far stranger than anyone imagined. The universe is not a smooth soup of evenly distributed galaxies. Instead, it resembles Swiss cheese. Dense matter forms walls and filaments surrounding enormous hollow pockets. This foam-like architecture is called the cosmic web, and it represents the largest structure in nature. Galaxy clusters concentrate at the intersections where multiple filaments meet, creating nodes of intense matter density. These nodes shine brilliantly with millions of galaxies packed relatively close together. Stretching between them run filaments, long chains of galaxy groups that can extend for hundreds of millions of light years. These filaments form walls, vast sheets where galaxies gather in higher than average concentrations. Between the filaments and walls lie the voids, taking up most of the volume while containing hardly any mass. This structure wasn't always obvious. For decades, astronomers photographed the sky and counted galaxies, but the true three-dimensional arrangement remained hidden. Distance measurements were poor. Galaxies that appeared next to each other might actually be separated by billions of light years, with one much farther away than the other. Only when scientists began measuring galaxy redshifts systematically in the 1970s and 80s did the cosmic web reveal itself. Redshift surveys allowed astronomers to calculate how far away each galaxy was by measuring how much the expansion of space had stretched its light toward redder wavelengths. Suddenly, the distribution snapped into focus. The universe had structure on scales nobody expected. The first major void discovery came in 1978, when two independent teams identified large underdense regions. More surveys followed, each mapping deeper into space and revealing an increasingly intricate web. The Sloan Digital Sky Survey, which began in 2000, created spectacular three-dimensional maps spanning billions of light years. These maps show the cosmic web in stunning detail. Filaments twist and branch like blood vessels. Voids appear as dark bubbles, sometimes 500 million light-years across. The largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light-years long. On the opposite end of the spectrum, supervoids like the Eridanus void stretch 1.8 billion light-years wide, with even fewer galaxies than the KBC void. Together, these features paint a picture of a universe organized on scales far larger than anyone predicted. Galaxies are not the fundamental building blocks. The web itself is the structure, with galaxies just marking where the matter happens to concentrate. Why does the universe organize this way? The answer reaches back to the beginning. Immediately after the Big Bang, matter was not perfectly uniform. Quantum fluctuations during the universe's first fraction of a second created tiny variations in density. Some regions were slightly denser than average, others slightly less dense. These differences were minuscule, maybe 1 part in 100,000, but gravity amplifies even tiny advantages. Denser regions pulled in more matter, making them denser still. Less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, this process snowballed. Small clumps merged into larger clumps, which merged into galaxy clusters, which aligned into filaments. Meanwhile, the underdense regions expanded into voids. The cosmic web is essentially gravity doing its work over cosmic time, turning barely noticeable initial ripples into the grandest architecture in existence. Today, voids occupy roughly 90% of the volume of space. Filaments and clusters make up the remaining 10%, but contain most of the mass. This imbalance defines the universe's character. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness punctuated by occasional concentrations of matter. The KBC void is just one bubble in this foam, but it happens to be our bubble. And that makes all the difference for what we observe and how we interpret the universe. The Milky Way is not at the center of the KBC void, but it's close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual center. That might sound like a huge distance, and it is compared to anything humans experience. But the void extends outward for 1 billion light-years in every direction from its center, making our offset relatively small. We sit well within the underdense region, surrounded by the void's low-density environment in all directions. This position is not random. It has consequences for every observation we make and every conclusion we draw about cosmology. If we were located outside the void entirely, in one of the dense filaments, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate, and the Hubble tension would not exist. Our larger cosmic neighborhood adds another layer to this story. The Milky Way belongs to the local group, a collection of about 80 galaxies, including our giant neighbor Andromeda. The local group itself sits within the Laniakea supercluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. Laniakea is enormous by any normal standard, yet even this supercluster resides within the KBC void. Think about that for a moment. A structure containing 100,000 galaxies still counts as part of an underdense region. The void is so vast that it can swallow entire superclusters and still have room to spare. Laniakea forms part of the sparse population of matter scattered through the void, one of the rare concentrations in an otherwise barren expanse. The local group is also influenced by another nearby void called the local void, which is distinct from but connected to the larger KBC void. The local void extends about 200 million light-years and sits adjacent to our position. Our galaxy is rushing away from it at 600,000 miles per hour, pushed by the gravitational pull from denser regions beyond. This motion is separate from the overall cosmic expansion. It's a peculiar velocity, meaning it results from local gravitational effects rather than the stretching of space itself. These peculiar velocities complicate efforts to measure the true expansion rate because they add extra motion on top of the expansion signal. Astronomers must carefully account for these local effects, but inside a supervoid, those effects are amplified and harder to separate cleanly. The void's influence reaches even farther. When scientists measure the motion of galaxies out to distances of 250 million light-years, they find bulk flows that exceed predictions from standard cosmology. Entire regions of space are moving faster than they should be, flowing in coherent patterns driven by the void's gravitational imbalance. The KBC void creates a large-scale velocity field that affects everything within it. Galaxies are not just sitting in an empty region, passively expanding with the universe. They're actively responding to the gravitational landscape, accelerating outward from the underdensity toward denser structures beyond the void's edge. This makes our local patch of the universe more dynamic and unusual than the calm, uniform cosmos that standard models assume. Our position inside the void also affects what we can see. Light from distant galaxies travels through the void on its way to our telescopes. That light experiences less gravitational interaction than light traveling through denser regions. The reduced gravity creates subtle effects on the light's wavelength and energy. Additionally, the void itself influences the distribution of matter we observe. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as a concentration of galaxy clusters and filaments at a specific distance range. Beyond the shell, the universe returns to more typical density. This creates an observational bias. We're not sampling a random location in the universe. We're sampling from inside one of its most extreme features. Living in the void means living with systematic uncertainty about how typical our measurements really are. Every measurement you've ever heard about the universe's expansion rate might be wrong, not because scientists made mistakes, but because we're measuring from inside a cosmic hole that distorts the signal. The problem reveals itself when astronomers use different methods to calculate the Hubble constant, the number that tells us how fast space expands. One method looks at the cosmic microwave background, ancient light from when the universe was just 380,000 years old. This light encodes information about the early universe's density and expansion rate. Scientists feed this data into cosmological models and calculate what the expansion rate should be today. The answer comes out to about 67 kilometers per second per megaparsec. That means for every megaparsec of distance, roughly 3.3 million light years, space expands at 67 kilometers per second. The second method looks at nearby objects with known brightness, specifically type Ia supernovae and Cepheid variable stars. These objects serve as cosmic measuring sticks because astronomers understand exactly how bright they should be. By comparing their actual brightness to their apparent brightness as seen from Earth, scientists calculate their distance. Combining distance measurements with redshift measurements gives the expansion rate directly. This local method consistently produces a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. That sounds small, but it represents a crisis. Both measurements are incredibly precise, with very small error margins. Both should give the same answer if cosmology is correct. They don't. This discrepancy is the Hubble tension, and it has reached 5 sigma statistical significance, meaning there's less than a 1 in a million chance it's just random variation. The KBC void explains why these numbers disagree. When we measure the expansion rate using nearby supernovae, we're measuring within the void. The void's low density means less gravity pulling back on the expansion. Matter from the denser regions outside the void gravitationally attracts galaxies within it, adding extra outward velocity. Galaxies appear to recede faster than they would in a typical region. This inflates the local Hubble constant measurement. We're not measuring the universe's true expansion rate. We're measuring the expansion rate plus the void's peculiar velocity field. The effect is large enough to account for most or all of the observed tension. When scientists model how a void of the KBC's size and depth would affect local measurements, they find it could boost the apparent expansion rate by exactly the amount needed to match observations. But here's where it gets uncomfortable. If the void explains our local measurements, then those measurements don't tell us about the universe as a whole. They tell us about our weird local environment. The cosmic microwave background method is unaffected by the void because it probes the early universe, long before voids formed. That measurement might be the accurate one for the universe's global properties. This means most headlines you've seen about the accelerating universe and dark energy might be describing a local phenomenon rather than a universal truth. We've spent decades building cosmological models based partly on local expansion measurements, and those measurements might be systematically biased by our location. Some scientists resist this conclusion because it violates the cosmological principle, the assumption that Earth does not occupy a special location. The principle states that the universe should look roughly the same from any vantage point once you average over large enough scales. Finding ourselves inside a supervoid that significantly affects our measurements seems to contradict that idea. It suggests we're in an unusual location, which makes physicists uncomfortable. Science has progressively decentered humanity from special cosmic positions. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of anything. And now we're supposed to believe we just happen to live inside one of the largest voids ever observed? The statistical improbability bothers many researchers, yet the evidence keeps mounting. The void exists. Our measurements are discrepant. The void's effects match the observations. Whether we like the implications or not, the universe might actually be lying to us about its expansion rate. Or more precisely, our location is causing us to misinterpret what we measure. Understanding how gravity creates this mess requires looking at how forces work in empty space. Gravity inside a void does something counterintuitive. It pushes outward instead of pulling inward. This isn't because gravity itself reverses. The force of gravity always attracts mass toward mass, but the geometry matters. Imagine standing in a shallow valley surrounded by mountains. Gravity pulls you toward the mountains, which means pulling you away from the valley center. Inside a cosmic void, galaxies experience the same effect. All the matter lies outside the void, in the surrounding filaments and clusters. That exterior matter gravitationally attracts the interior material, pulling galaxies outward from the void center toward the denser regions beyond. The result is an outflow, a systematic pattern of galaxies accelerating away from the underdense region. This outflow is measurable and significant. Astronomers can track galaxy velocities using redshift measurements combined with distance estimates. When they map velocities around known voids, the pattern is clear. Galaxies near void centers are moving faster outward than cosmic expansion alone predicts. The effect is strongest near the void center and weakens toward the edges where matter density increases. For the KBC void specifically, the outflow adds hundreds of kilometers per second to galaxy velocities within the void. Our own galaxy participates in this pattern. The Milky Way is moving at 600,000 miles per hour away from the nearby local void, driven by the gravitational imbalance. This motion combines with other local effects, like the gravitational pull from the Virgo cluster, to create our galaxy's overall peculiar velocity. The outflow has implications for cosmic expansion measurements. When we observe distant galaxies and measure their redshift, we're seeing a combination of two effects: the expansion of space itself and the peculiar motion of galaxies due to gravity. Normally, scientists can separate these components because peculiar velocities average out when you look at large enough volumes. For every galaxy moving toward you due to local gravity, another galaxy is moving away, and the average is 0. But inside a void, the peculiar velocities don't average out. They all point in the same direction, outward. This creates a systematic bias that inflates the apparent expansion rate when measured from within the void. The problem compounds at different distance scales. Close to the void center, the outflow is rapid. Farther from the center but still within the void, the outflow is slower. Beyond the void's edge, the peculiar velocities might even reverse as matter falls back toward the denser filaments. This creates a complicated velocity profile that varies with distance. When astronomers measure the Hubble constant using supernovae at different distances, they're sampling this varying velocity field. If most of their supernovae lie within the void, which they do, because we deliberately avoid using extremely distant supernovae due to other complications, the measurement gets boosted by the outflow. The farther out you measure, the less the void affects the result. This predicts that the Hubble constant should appear to decrease with distance. Recent observations confirm exactly that trend. Modeling these effects requires careful calculation. Scientists must estimate the void's size, depth, and density profile, then calculate the gravitational potential it creates. That potential determines how fast material flows outward at each radius. The calculations show that a void roughly 1 billion light-years in radius with a 20% density deficit can easily produce the observed velocity anomalies. The match between predictions and observations is good enough that many researchers find the void explanation compelling. However, the standard cosmological model struggles to explain how such a large void formed in the first place. Computer simulations based on lambda-cold dark matter rarely produce voids this extreme. When they do, it requires very specific initial conditions that are statistically unlikely. This raises a troubling possibility. Maybe our cosmological model is missing something. Our motion through this gravitational landscape is faster than anyone expected. The Milky Way is not sitting still in space. It's plummeting through the cosmos at 600,000 miles per hour, roughly 850 times the speed of sound. This velocity is not from the expansion of space, but from local gravitational effects. Specifically, our galaxy is being pulled away from the local void and toward the denser structures beyond it. The local void is distinct from, but connected to the larger KBC void, and it exerts a strong influence on our motion. The void itself is not pushing us. Rather, the deficit of matter in the void means there's less gravity pulling us toward it compared to the gravity pulling us in other directions. The denser regions win the tug-of-war, accelerating our galaxy away from the underdensity. This speed is difficult to comprehend. 600,000 miles per hour means the Milky Way travels about 167 miles every second. In a single year, our galaxy moves about 5.2 billion miles through space relative to the void. But even at this breakneck pace, the void is so vast that our motion barely makes a dent. It would take hundreds of millions of years to cross from one side of the void to the other, even at this speed. Meanwhile, the void continues expanding due to cosmic expansion and dark energy, growing faster than we can escape it. We're inside the void now, and will remain inside it for the foreseeable cosmic future. The local sheet adds another component to our motion. The local sheet is a flattened structure of galaxies that includes the Milky Way, Andromeda, and other nearby galaxies. This sheet forms one wall of the local void. The entire sheet is rushing away from the void center at about 260 kilometers per second, roughly 580,000 miles per hour. Our galaxy participates in this bulk motion along with its neighbors. The sheet is not static. It's actively being evacuated from the void region, flowing outward like water draining from a depression. This motion has been ongoing for billions of years and will continue for billions more. But there's more to our velocity than just escaping the void. The Milky Way is also falling toward the Virgo cluster, a rich concentration of galaxies about 60 million light-years away. The Virgo cluster contains over 2,000 galaxies and has enough mass to gravitationally attract everything in the surrounding region, including us. This adds another component to our peculiar velocity, roughly 250 kilometers per second directed toward Virgo. Meanwhile, the Milky Way and Andromeda are falling toward each other and will collide in about 4 billion years. That motion adds yet another velocity component. When you add up all these gravitational influences, the Milky Way's total peculiar velocity relative to the cosmic microwave background rest frame is about 627 kilometers per second. These motions matter because they complicate cosmological measurements. When we observe distant galaxies and measure their redshift, we need to correct for our own motion through space. Otherwise, galaxies in the direction we're moving appear blue-shifted, and galaxies in the opposite direction appear red-shifted, creating a false pattern that mimics cosmic structure. Astronomers have known about these corrections for decades, and routinely apply them. But inside a void, the corrections become more complicated because the void itself creates large-scale bulk flows that extend over hundreds of millions of light years. Disentangling the void effect from the true cosmic expansion requires careful modeling of the local velocity field. Our high speed through space is itself evidence for the void. If we lived in a typical region with average density, our peculiar velocity would be much smaller, maybe 100 or 200 kilometers per second at most. The fact that we're moving so fast indicates strong gravitational gradients in our vicinity, exactly what you'd expect from being near a large underdense region. The velocity is consistent with the void hypothesis and would be difficult to explain without it. This makes our motion a key piece of evidence in the debate over whether the KBC void exists and whether it affects our measurements. The universe may be lying to us about its expansion rate, but it cannot hide the fact that we're racing through it at incredible speed. The voids we observe today began as infinitesimal quantum ripples in the first moments after the Big Bang. During a period called inflation, the universe expanded exponentially for a tiny fraction of a second, perhaps 10 to the minus 35 seconds. During this expansion, quantum fluctuations were stretched from subatomic scales to cosmic scales. These fluctuations created slight variations in the density of matter and energy. In some regions, density was a tiny bit higher than average. In others, it was a tiny bit lower. The variations were incredibly small, about 1 part in 100,000. But they were enough to set the stage for everything that followed. After inflation ended, the universe continued expanding, but at a much slower rate. Matter began to clump together under gravity, and gravitational pulling only amplified the initial density differences. Regions that started slightly denser attracted more matter from their surroundings, making them denser still. This created a positive feedback loop. The denser a region became, the more strongly it pulled matter toward itself. Over millions of years, these overdense regions collapsed into the first stars, then galaxies, then clusters of galaxies. Meanwhile, regions that started slightly less dense lost matter to their denser neighbors. As matter drained away toward the collapsing overdense regions, the underdense regions became even emptier. These underdense regions evolved into voids. The process is called gravitational instability, and it turned barely perceptible initial ripples into the dramatic large-scale structure we observe today. The cosmic microwave background radiation provides a snapshot of these density variations when the universe was only 380,000 years old. At that time, the variations were still tiny, visible only as slight temperature differences of about 100 millionths of a degree. But those temperature differences correspond directly to density differences. Warmer spots had slightly higher density. Cooler spots had slightly lower density. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft have mapped these temperature variations in exquisite detail across the entire sky. The maps show a modeled pattern of hot and cold spots at various angular scales. This pattern encodes the seeds of structure formation. Scientists can take this pattern and run it forward in computer simulations to predict how structure should look billions of years later. Those simulations reliably produce a cosmic web of filaments, clusters, and voids that closely resembles what we observe. The match between predictions and observations is one of the great successes of modern cosmology. It confirms that our understanding of how gravity shapes structure over cosmic time is largely correct. However, the simulations rarely produce voids as large or as deep as the KBC void. This is where tension arises. The initial quantum fluctuations were random, so every region had some chance of ending up as a void or a filament. but probability distributions matter. Small voids should be common. Medium voids should be less common. Extremely large voids should be very rare. The KBC void appears to fall into the extremely rare category, which raises questions about whether our simulations are missing something. The quantum origin of voids is both elegant and unsettling. It means that the cosmic desert we inhabit traces back to subatomic processes that occurred before atoms even existed. Randomness at the smallest scales propagated upward to create structure at the largest scales. The universe's organization is not designed or predetermined. It's the consequence of random quantum fluctuations amplified by gravity over billions of years. This realization is one of the profound insights of modern cosmology. But it also means that our location within this structure is the result of chance. There's no reason we had to end up in a void rather than in a filament. We're here because the initial conditions in our region happen to be slightly underdense. That accident of quantum chance 14 billion years ago determines what we observe when we look out at the cosmos today. When you picture the universe, you probably imagine a sky full of stars and galaxies, but the reality is the opposite. The universe is overwhelmingly empty. Voids occupy roughly 90% of the total volume of space. Galaxies and galaxy clusters crowd into the remaining 10%, packed into filaments and walls that surround the voids. This is not just empty space in the sense of vacuum between stars. It's empty in the sense that entire regions, hundreds of millions of light years across, contain almost no galaxies at all. If you could travel through a void, you would fly for tens of millions of years at the speed of light without encountering a single galaxy. The isolation would be nearly absolute. This distribution creates a lopsided universe. Most of the matter concentrates in a small fraction of the volume. The filaments are crowded with galaxies that interact, merge, and evolve rapidly. Star formation is vigorous. Black holes grow. Galaxies collide and trigger bursts of star creation. Meanwhile, the voids are quiet. A few lonely dwarf galaxies drift through the darkness, separated by vast distances. These void galaxies evolve slowly because they rarely interact with neighbors. They tend to be smaller, fainter, and less evolved than galaxies in dense regions. Star formation is sluggish. Many void galaxies contain large amounts of neutral hydrogen gas that has not yet condensed into stars. They are galactic backwaters, isolated from the busy highways of the cosmic web. Even in voids, dark matter is present. Dark matter makes up about 85% of all matter in the universe, but doesn't interact with light, making it invisible to telescopes. It's detectable only through its gravitational effect. In voids, dark matter is much less concentrated than in filaments, but it still exists at about 15% of the cosmic average density. That might sound like a lot, but spread over such huge volumes, the amount of dark matter per cubic light year is incredibly tiny. Additionally, voids contain dark energy, the mysterious component driving cosmic acceleration. Dark energy appears to be uniform throughout space, so voids have just as much dark energy per volume as dense regions. In fact, because dark energy doesn't clump like matter, it becomes the dominant component in voids where matter is scarce. The interplay between dark matter and dark energy determines void evolution. In the early universe, matter dominated even in underdense regions, and gravity still mattered. As the universe expanded and dark energy became more important, voids began accelerating their expansion. This acceleration makes voids grow faster over time, eating into the surrounding filaments. Eventually, if dark energy continues to dominate, voids will consume more and more of the universe. Filaments will thin out. Galaxy clusters will become isolated islands in an ever-expanding sea of emptiness. So what does it mean that we live inside one of these cosmic deserts? First, it means our view of the universe is biased. We're not observing from a typical location. We're observing from one of the emptiest regions that exist. Every measurement of cosmic expansion, every calculation of dark energy density, every inference about the universe's fate, all of it might be skewed by our unusual vantage point. Second, it suggests that Earth's existence might be tied to this location. Perhaps life requires a certain type of environment to emerge. Maybe moderate underdensity is actually favorable for habitable planets. If so, we shouldn't be surprised to find ourselves in a void, because that's where observers like us can exist. This is a weak anthropic argument, and it doesn't fully explain why we're in such an extreme void. But it does suggest that our location might not be as improbable as pure statistics would indicate. Third, it reminds us that the universe is far stranger and more varied than we often assume. The cosmos is not a uniform backdrop for galaxies. It's a dynamic, structured entity with regions of extreme density and extreme emptiness. We happen to inhabit one of the extreme regions. The story of the cosmic void is ultimately the story of our cosmic humility. Just when we thought we understood our place in the universe, we discovered we're falling through a hole in space 2 billion light-years wide. Just when we thought our measurements of cosmic expansion were reliable, we learned they might be distorted by our location inside an underdense bubble. Just when we thought the cosmological principle assured us that Earth occupies no special position, we found ourselves near the center of one of the largest voids ever observed. The universe is not lying to us. It's simply more complex than our models assumed. And we're learning that our perspective, from inside this cosmic hole, colors everything we think we know about the cosmos. Understanding the void doesn't diminish the universe. It reveals just how vast and intricate reality truly is. We live in a cosmos where 90% of space is emptiness, where quantum fluctuations from the Big Bang grew into structures billions of light years across, where our entire galaxy races through space at 600,000 miles per hour, fleeing from underdensity. We live in a universe far stranger and more magnificent than we ever imagined. And we're only beginning to understand what that means.